Hi there, my name is Charles Msipa. Welcome to another presentation on elements of matrix analysis. Today our discussion focuses on state space representation. This has got its origins in the fact that previously we should have seen how we can reduce the solution of a differential equation of order n to solutions of n first order differential equations with the initial conditions. In this presentation, we attempt to give a feel of how we can reduce this problem to applying matrix techniques. In other words, we take a modeling differential equation, now a differential equation modeling a system, and represent it in matricial form and the form of the solution, the system of equations generated has. So let's start. In this case, we're looking at a single input, single output system, which is abbreviated as SISO. So starting with that, let's say we're given an equation of order n, in this case an, dn, dy, dt, n minus 1, n minus 1, dy, dt, n minus 1. Here it is d power n plus dash 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 up to a1 dy dt plus a0 y equals to input u. So now what we have here is an equation of order n where the ai coefficients, some of them can be 0, but if we consider this to be the equation of order n, we consider that an is different from 0. And the initial conditions which will be given in this case will be initial conditions y of 0, y prime, now the first order derivative, up to the derivative of order n minus 1 at 0. These conditions will be known, and to represent the system, this differential equation in a state space representation, we introduce new variables here, which we can call x1 at t, x2 at t, up to xn at t. These functions actually form what we call a state space vector. So what we do here, we introduce this variable. In this case, we declare x1 of t to be equal to the unknown function in this differential equation, in this case, which is y. As you can see, it's dy to order n of y dt up to n. So we declare this to be equals to y of t. And then our x2 is taken to be the derivative of y with respect to t. In this case, this will be the derivative of x1, which we're going to denote here as x dot for denoting the derivative in short form. Now, continue with this. We have x3 of t equals to the second order derivative of y with respect to t, which is actually our first derivative of x2. Now, this process continues this way until we get to the variable xn of t, in this case, which is going to be the derivative of order n minus 1 of y with respect to t n minus 1. And then this, like we can see here, x3 is the derivative of x2, which is 2 being 3 minus 1. So here we're going to have here x to the power n, sorry, x n minus 1, first order derivative as a function of t. Now, when we get here, we'll see that if we differentiate this derivative, we're going to get the nth derivative there. That is very important. Okay, now to reorganize this, having declared this variable this way, we can rewrite this given differential equation of order n as follows in terms of the variables, in terms of these variables. In other words, we can do this. We know that our y is our x1, so we can rewrite this as a0 x1 equals to our input here, that plus a1, which is our x2, plus, in this case here, this is our xn minus, this is our xn, a n minus 1, plus, now as you said before, now if we differentiate this derivative, which is xn, we'll get our nth order derivative there. Then we're going to put this as x dot n by an. So now this is the equation now written in terms of the new functions here, x1, x2, x3, xn. Let's put it this way. So now what you can now do now, we can get a new representation of this equation as follows. But first of all, let's note that this statement is, this expression is equivalent to saying xn prime is equals to an minus 1 over an, sorry, with a minus sign there. Now we're making subject the formula x n there, then multiplied by x n minus a n minus 2 over a n multiplied by x n minus 1 minus also minus paste there, minus a1 not an, a1 over an x2 minus a0 over an x1 plus 1 over an u. So in this expression we've left out the t's just for simplicity of writing. Okay, now we can now represent this equation, this differential equation, with the following system of equations. Let's open some space here and say now what we did is we said x1 prime was equals to x2. Now our declaration was like x1 prime was equal to x2. What you can say here, what you can write next in necessary, you can say now here this is equals to 0x1 plus x2 plus 0x3 plus dash up to 0 plus 0xn. I'm writing these zeros so that at the end you can easily see where you are going to, but what is important is that this still we have what we said before, that x1 prime is equal to x2. So for now we can forget about these zeros, but you will see how they are useful at the end. Then our x2 prime was equal to x3, so you can write that here is plus x3, which means that you put quotient 0 for x2 and the quotient 0 for x1, and that's that, plus the rest of 0 coefficients plus 0xn. Similarly, x3 prime will be equals to x4, then we'll be having 0 x3 plus x4 plus up to 0 xn. On this side we're going to have 0 x2 0 x1. So we'll continue this up to xn prime, and now we can reorganize this and start with x1 just to be sort of have the same organization for these variables x1, x2, xn. So we're going to have here minus x0 over xn, so over an, sorry, x1 minus a1 over an x2 minus, continuing there up to minus an minus 2 over an minus an minus 1 over an x n, and here we're missing x n minus 1, so let's correct that. That will be minus a n minus 2 over a n x n minus 1. I hope you see that these variables now are organized x1, x2, x3 up to xn, and the x1, x2, x3 up to n. And then here to be plus 1 over a n by u. And now you can see that the previous terms are stopping in this column, but they don't have this. So what you can do, just to make it sort of uniform, you can put here u, 0u plus 0u plus 0u. Now that system which we represented this way, you will see in your text these zeros are not written, but I write them because I want to easily see what I want to see next. So now what we have in this representation is that we have got first order derivatives here in a column form, which we can put in a column form as x1 prime, x2 prime up to xn prime, and you can put that as a column matrix this way. And also here you can divide this into two blocks. In this case, the block of xn's from here to there, and then the block of u's here. What we have here is that you can write this again as a similar column matrix like this, whereby the first entry there is this sum, which is 0 x1 plus x2 plus 0 x3 plus dash up to 0 xn, and you can close there and then say plus here. You put again another, which is 0u and 0u dash dash up to 1 over an u, and put that. Now here we can fill up. Now it says 0 x1 plus 0 x2 plus x3 plus 0 x4 up to 0 xn. Then lastly we're going to have minus a0 over an x1 minus a1 over an x2 dash dash there up to minus a n minus 2 over a n x n minus 1 minus a n minus 1 over a n x n. It's a bit crowded there, but I hope you can see. This is here xn. Now, maybe when you're doing this exercise, you will not have to do exactly as I'm doing it here, because I'm trying to explain and trying to make you see what at the end of the day you end up with here. Now, with these three blocks, what we should do now is to focus on this middle one, because these ones are simple. Here, what we can do, we can actually take out common factor u here and leave 0, 0 dash dash 1 over a n multiplied by u. Sorry, these are dashes, not ones. This gives this dots. So n rows there. Now, this side we've got again a column vector of derivatives. And we've got there comes to x n. Now, coming to the center here, I hope you can see that we've got some kind of, we've got actually not some kind of, we've got exactly what we have as multiplication of matrices, whereby we've got this square matrix multiplied by vector x1, x2, column vector x1, x2, x3 up to xn, which if you want to rewrite this in matrix form as a multiplication of matrices, you can rewrite this as then here what we're actually doing, we're undoing matrix multiplication I hope you can see that if we take this column over there and we've got n rows here, we've got n columns here and n rows there, so the multiplication is possible. So what's going to happen, you're going to have an entry 0 there for that, and an entry 1 there, and then 0. The rest are going to be zeros up to the n column. Next row will be 0, which is the coefficient of x1, and another 0, and then 1 for the coefficient of x3, and then what are going to follow there are going to be zeros. Then continuing with that, at the end you are going to have minus a0 over an, then minus a1 over an, then dash dash up to minus an minus 2 over an, and lastly an minus 1 over an. Now, if we look at this, the differential equation which we had, we've actually represented here in a matrix form. So what we have here, you see, you note that here we've got a vector which is consisting of entries which are derivatives, and here we've got our state vector x1, x2 up to x3. Now what we can now do is to simplify this and write it as x to represent this vector plus equals to this matrix here. We're going to denote it by A, and the vector here x, and this column vector which we've represented here multiplying mu, we're going to represent it by a small letter B, and that by u. And then I repeat here that these are going to be called state variables, and they can put here a state vector. And once we've represented this system this way, now remember at the beginning we said y was equals to x1, which you can also expand conveniently to say this is x1 0 0 up to n columns there. And then if we now try to put this more explicitly, we can transform this to saying here we've got a vector 1, a column vector 1 0 0 up to that, and then consider that this is a multiplication of a vector, a state vector, which is constant of x1, x2. Oh, sorry, I think I made a mistake here. This should be, I should have written this as x1 plus 0, x2 plus 0, x3 plus dash dash up to 0, xn. Now looking at the coefficients there, those are the coefficients we're leaving here as a row vector, and multiplied by the state vector which goes up to xn. But because we're considering these vectors here as column vectors, then we're going to take this one as we're going to take this vector as a transpose of a column vector, because it is a row there. Then writing this in general, this is going to be written as C transpose multiplied by the vector S, the state vector representing this component, and then C will be the column vector consisting of n rows, which is 1 0 0 dash dash up to 0 up to nth row, and that. So now having this y in this way, and thus we can now represent what we call the state space representation of a dynamic system as x dot equals to ax plus bu and y equals to c transpose multiplied by x, which we have this one. And this is what we call the state space model, representing the system which was modeled by the given differential equation. At this point, I think when you, I understand that the explanation is a bit long, but you can go over it again and see exactly how we get here. But I think what will make this more clear is to take an example. Let's now take an example of an equation and reduce it to this kind of representation. Get the fresh page here. Let's say we're given an example. Let's say the order of the exercise says obtain a state space representation of the system characterized by the third order differential equation, which is the following: d3y dt plus 3d2 dt squared plus 2 dy dt minus 4y equals to e minus t. So now our solution will be as follows. Now as we're repeating the previous process with a particular example. So what I'm going to do, we declare our x1 equals to y like before. Then our x2 is going to be the derivative of y, which is dy dt, and this is our x1 prime. Now, doing like we did before, we can now say this, taking that is equal to x2, we can actually say this is 0 x1 plus x2 plus 0 x3. Like I said before, you might not need to do this one always, but for this first example, I want to make it as suggestive as possible what you must do. Now, x3 will be equal to our second order derivative with respect to t, which is actually going to be our x2 prime, and as you can see is x3, which means you get 0 x1 plus 0 x2 plus x3, and then lastly we're going to have our x3 prime, our x3 prime will be actually this derivative. So making it subject to the formula, we're going to end up with something like 4y, which is going to be 4x1 minus 2 dy dx, which is going to be minus 2x2, then minus 3x3 plus e to the power minus t. Again, there at that point, we can now say this is 0, e minus t, and this plus 0, e minus t. Here we're adding this just to make it very visible what we need here. So as you can see, we got 3 blocks here. The block of derivatives, this block of what we can look at as if we put a matrix brackets here, is a multiplication of a matrix 0, 1, 0 by the vector x1, x2, x3. So now picking on this one, that and that, what we're going to have is the following. Let's number this for visibility: block 1, block 2, and the block 3. Now organizing that, we're going to have x1 prime here, x2 prime, x3 prime. What we're doing, we're just reproducing this block but in a matrix form, organized in matrix form. Then we collapse all these equal signs to one equal sign, because now we're talking about equality of matrices here. Then the second matrix here will be 0, x1 plus x2 plus 0, x3, and then 0, x1 plus 0, x2 plus x3. Then you've got here 4, x1 minus 2, x2 minus 3, x3 plus 0, e power minus t, 0, e power minus 3, and e power minus t, and that. So clearly in this middle block, we can see that we can undo this multiplication of 2 matrices. Then we end up with the following. Let's say repeat this: x1, x2, x3, and all these are derivatives, equals 2 brackets here now, leaving the only coefficients in this matrix get 0, 1, 0, 0, 0, 1, 4, minus 2, minus 3, and here we've got this first vector, which is x1, x2, x3, close there, plus 0, 0, 1, multiplied by our input function, which is e to the power minus t. Then now finally we have x for this vector plus A for this one, X plus our B U T, well, UT is that. Then our Y in this case, Y was equals to X1. Again, we can start by putting Y is equals to X1 plus 0, X2 plus 0, X3. That is just for explanation. So now I'm doing that. You can see we're left with a vector which is 1, 0, 0 multiplied by X1, X2, and X3, whereby this is our C transpose multiplied by X. So then this becomes our state space representation of the system, which was represented by a third order differential equation given there. So I hope you'll be able to go through this example slowly and this previous explanation and be able to take a fresh exercise from your textbook and to be able to achieve similar results. Otherwise, for now, thank you for listening.